All right, good morning. So this is going to be lecture number 8, which is going to be about polynomial regression. Before we jump into the lecture, just a couple things. So just some broad stroke logistics about exam number 1. It'll be there on February 14th. The exam itself will be conducted online, so you'll find the questions online on Canvas. More details I'll provide it soon. I'm still in the process of constructing the questions. So the numbers that you see over here are, again, it's broad stroke logistics rather than something very specific. So at this time, I'm thinking you're going to have like a 2-hour window to take the exam, anything between 9 o'clock to 11 o'clock next Wednesday. The exam itself will be around 75 minutes, which is the length of the class itself. But I do realize that there'll be some logistics in terms of uploading your work. So maybe we'll have a 15 minutes extra for that. I'm still working on that logistics part, and I'll let you know. But this is for the in-person students. For the distance learning students, you'll have until the weekend in order to take your exam. That is, your window will be until the weekend, but the exam itself, you need to finish it within 75 minutes, which will be the same between distance learning and Atlanta students. The questions are going to be analytical, so you don't need a Google Colab, you don't need a notebook in order to find your solutions. Everything is going to be analytical. That basically means that it might be true-false questions, there might be a few math-related questions, but nothing too deep. It won't be anything that you wouldn't have seen, let's say, during either homework or during the lectures itself. So it won't go too deep into the theory or the math portion. It's more of a broad strokes approach into the conceptual part of what we would have learned. I do give an example here in terms of the kind of coding questions that you might get. We'll give you a code, and that code you might have to analyze it to say that, okay, this might be the output, or this is the concept that I'm using, this is the algorithm that I'm using within the code, and so on. Either way, so it won't be anything coding heavy. You won't have to actually open a Google Colab notebook. You can, of course. It's going to be an open book, open notes question, so anything and everything is going to be allowed, but you don't need to. There's no coding heavy questions that you're going to find within the exam itself. So again, this is more broad strokes. By the end of this week, and definitely by Monday next week, I'm going to post a set of more detailed logistics and instructions that you're going to be using in order to solve for the exam. Any questions about the exam logistics itself? I forgot to mention, the materials themselves will be from lecture number 1 to lecture number 7. 7 is linear regression. So last week's video lecture that I posted on Wednesday will be the last part of the portions for this particular quiz. Yes? Yes, so we'll release it. So currently the distance learning students will be submitting it today. We have a couple of students who will be submitting tomorrow as well. So by Wednesday, we will release the homework solution set. Just one thing about homework 2 as well. Thank you for bringing it up. So the policy that we'll be using will be that if you miss by one day, you lose 10%. If you miss the next day, you lose 10%. It's just a linear increase. So you lose 20%. If you submit it on Tuesday, for instance, you'll be losing 20%. This is for in-person students. You'll be losing 20%. But then by Wednesday, as soon as we release the solutions, that will be it. We won't accept any answers, essentially, your solutions by the time that we release the actual answers to the questions. So 20% is the maximum you'll lose for homework number 2 if you decide to submit it by the end of Tuesday. There's a couple of students. I did get a couple of emails, but I haven't replied back yet to those emails. So that is about homework number 2. If there are no more questions about the exam, we can move on to the lecture itself. All right. So just very quickly, what we covered, or at least the video lecture that was posted on Wednesday, covered some very simple things about linear regression. Now, as I mentioned on Wednesday, the class here is a little bit nonlinear. In many machine learning courses, what you'll see is that the first thing you learn is in fact regression, linear regression, then we move on to polynomial regression and all the other concepts of regression before moving away into classification settings. But the problem in that case is that we'll never be able to come to, let's say, something like deep learning or machine learning or more advanced concepts by the end of February and in March. Your first two homeworks would be very math related in that case if we are doing regression. So classification, once we did classification, at least now you're more exposed to scikit-learn and all these other concepts that exist. But there are concepts within homework number 2 which were not covered in the beginning part of the course. So many things that we talked about on Wednesday is something that was there in homework number 2. For instance, the definitions of epoch, with definitions of iterations, the fact that we're using bias within the X, which is the data itself, is not very intuitive concepts to start off with in classification. But as soon as you come to regression, it becomes a little bit more understandable. So we did talk about quite a few things. Hopefully you've seen the video that was posted on Wednesday. Many of these things that I just discussed was talked about on Wednesday. We'll keep that in mind, by the way, while actually grading the homework. So homework 2 will be graded more leniently based on the fact that some of the non-linearities within the way the course is structured is a challenge, especially for homework number 2. So what we saw during linear regression on Wednesday was this idea that we defined something called a different concept within machine learning, which was regression. The idea is that all x's are related to a certain distinct y, and this y is continuous. We think of y as a set of classes in classification. It's a target that we want to get towards. If given an image of a cat, the output has to be a cat. In regression, it's not like that. In regression, every single output is a continuous variable. It could be something like 4.34, 4.345, 4.3456, and there can be these n number of continuous distributions that we want to model. The goal in regression is to model that continuous distribution. One concept that we discussed was the idea of something called residual error. In classification, whenever we have your output y equals w transpose x plus b, we always associate the plus b as something called a bias. We want that to be the intercept within the classification framework. But in regression, when we talk about this sum concept that is adding to my class, which is weighted by theta, we think of that as an error, as some kind of a residual error. And when you look at the definition of regression, hopefully this should be clear. If I go back to what I was discussing last time, you have these ideas of ordered pairs where every single x1 has an associated y1, and there's an x2 and an associated y2, x3 and an associated y3. So if you have a million such data points, features x, it has a million such outputs in this regression framework. So the idea is that when you have all these data points that exist in this kind of a setup, the goal is to have a function that models this data, right? So it's not some classification framework that finds the maximum margin between data points, but it is a function f which models this data. So something of that sort could be this. This could be one function f that given x, it's able to model y. So for instance, when you're given a new point, so this is, let's say, at training, you have all these instances, but then you're given a data point called x, m, y, m, and this is at test time, and this point is somewhere here. X, M, Y, M. I'm just giving an example over here. You'll know exactly where this point is based on the training distribution and how it relates to that training distribution. Given just an XM, I will be able to find YM in regression framework because I have access to this line, this f of x that I have learned before from my training distribution. Now, if I did not have an error function, which was the epsilon in my training network, what would have happened is my output would be something like, my f would be something like this. Of course, it probably would have been more, more of a causewave function kind of a thing with more smoother edges, but essentially what it was going to do without the epsilon is it'll try to model every single data point within my function. In other words, it's memorizing where all these data points are, and given this x point, it won't have enough knowledge in order to model it. So for instance, if I have something like this, and this would have been your data point, it probably at this point has learned that it needs to go in a zigzag fashion. So any xm that it's going to find after, it's going to model it somewhere at this point. It doesn't know how to model the new point, because what it has learned is something that we are going to be calling as overfitting to the training data. It has overfit to the training data without actually learning anything new. So we're going to discuss quite a bit about optimization today and on Wednesday. The only thing that differentiates between optimization and learning is this very simple fact that we are using some kind of an error or some kind of a regularization, so that we don't learn everything there is to, or we won't overfit to the training distribution. Rather, we learn something from our training distribution. And that's why this idea of an epsilon in your error is very important. In fact, in the next slide, when we discussed how to formulate our cost function, everything was dependent on the epsilon, right? We started by saying that we're going to assume some kind of a distribution on epsilon. This is going to be a normal distribution. And the good thing is that if my x theta are deterministic, then y, which is also going to be a random variable, is going to depend on epsilon, because epsilon by itself is a random variable which has a probability distribution function associated with it. So y also has the same probability function associated with it. It is also going to be a random variable. Once it is a random variable, then we went through this process of trying to find, okay, how can I model this likelihood for this probability, which is my y? And we came to this likelihood function, which I'm putting it in a box over here, where it's a very nice formulation where your likelihood is now a function of yi minus theta transpose xi whole square. So it's like a least sum. So this formulation, yi minus theta transpose x whole square, is something that we're going to be calling a least squares function, formulation of a loss function. It's because essentially it's a square function. Instead of taking a root, we are taking a square function across the error. This yi minus theta transpose x is by itself a very simple error, which is just a subtraction, and we are taking a squared version of that. And once you have access to this, again, it's very difficult to look at the pi, which is the multiplication across different features. So what we do is, instead of taking likelihood, we take a log likelihood. And the good thing about log function is that it's monotonically increasing or decreasing. So minimizing the likelihood is the same as minimizing the log likelihood, or otherwise as well. Maximizing the likelihood is the same as maximizing the log likelihood. And we end up with a nice equation that is there at the bottom. Finally, what we saw was that the way we optimize towards getting the best optimal parameters theta, there's two ways of doing it. One, what we have seen before, which was the gradient descent methodology, where we'll be finding the gradients. We'll see if this gradient is less than 0, greater than 0, and try to come to a position where the gradient is 0. We try to optimize towards this point where gradient is going to be 0. The other one, which we found, in this case, the one that we used was an analytical solution. That was a normal equation. Using a normal formulation for the least squares cost function, we were able to derive an exact solution to the most optimal set of parameters theta. Again, all of this, the normal equation happened because of 2-3 things. The most important of which was we defined this kind of a Gaussian distribution on the epsilon function, which was the error function, and used that in our analysis in order to find the optimal parameters. Any questions before we move on to the other parts of this lecture? This was more of a recap in the video that was there on Wednesday. All right, so today what we'll be looking at is high degree polynomial regression. So what does that mean? Last Wednesday when we covered, by definition, we were looking at relationships that were linear. That is, my x's and y's had a linear relationship to it. In other words, a single line with some sort of noise was able to model the relationship, right? If you look at this particular graph here, there is no way that we can get a linear line that is going to model all possible data points within this framework, right? So it's very clear that looking at this, at least, it's more of a parabolic relationship. So it's something like this. It's a parabola. That is a relationship that exists between my x's and y's. All my ordered pairs belong to this relationship. So linear models cannot account for this relationships. Hence, we move on to something called non-linear regression in this particular case. So let's go back a little bit and think about what we did when we had this non-separable data in SVMs. The first thing that we did was have this kind of a soft margin classifier, right? We said it's okay to have multiple errors. So we had a tolerance limit that we were using. And the second thing we did was have something called a kernel function on top of our data. Instead of looking at x's as they are, as just a set of points in my coordinate space, I define a function that is given by k xi xj, which is phi of xi transpose phi of xj. It's a function that I use on top of my data points in order to move to a different representation space. And hopefully, in this representation space, my data is easily classifiable. At least that is what our hope was in SVMs. And in many cases, that turns out to be true. In most cases, in a low-dimensional space, a lot of data is non-separable. But as soon as you move to a different, higher-dimensional representation space, it becomes a bit more separable. And that is what we used in SVM. We'll use a very similar trick here in polynomial in regression as well. And what we'll be calling it is polynomial regression. The goal, again, is that, yes, in my coordinate space, in the space that I was given my data in, it's non-separable and it is non-linear, but there is a higher dimensional representation space where I can get a simple linear regression algorithm in that other representation space. So that is the goal that we'll be using in this case as well in non-linear regression. So this phi of x is some kind of a non-linear feature transformation that we are going to be doing on input x. So phi is where the non-linear relationship comes from. We're not modeling, even though this is nonlinear regression, we're not looking at the function itself as a nonlinear function. We are looking at some transformation on the data that we'll be using in order to create a nonlinear regression framework. That differentiation is very important because later on down the line, it will be the opposite. We'll directly look at nonlinear functions. So we'll do the exact same trick what we did last time, which is instead of looking at as a set of different functions, it will be y equals theta transpose phi of xi. Of course, there is always an epsilon associated with it, but essentially what we are doing is putting all the bias terms and the weightage terms within a single variable that we are going to be calling theta. And this theta, instead of multiplying xi directly, it'll be multiplying phi of xi, which is this nonlinear transformation or this kernel on top of my data point itself. If I try to put this mathematically, your phi of xi is given by 1 phi of x1, x2 until some xi. So in this case, we are looking at m type of nonlinear functions, transformations, and the data points itself, there are about xi features within this data. Theta, of course, is your weight functions, which from before is the w and b that was combined into this one parameter set, which we'll be calling as theta. So this was more of a general introduction into nonlinear regression. But then by the choice that we are making for phi, which is our kernel function, we can have multiple different kinds of regression possible. Going back to SVMs, there was multiple things there as well, right? There's something called radial basis functions that are very common in SVMs that we use, where the kernel itself was some kind of a Gaussian distribution, or there was a polynomial function that we were using as a kernel. But we didn't explain too much about it at the time because it makes a little bit more sense when we are discussing about kernels from a regression setting than being introduced to it directly in a classification setting. So what is polynomial regression? The idea is that by just looking at this, for instance, this is a pretty straightforward graph that you're seeing here. It's very clear that by looking at it, it is a parabolic function. So my output y has to be a function of a of x squared plus b of x plus c with some random noise that is added. That is how this set of data points were generated. Right? So given this kind of a function, a of x squared plus b of x plus c, we'll be able to model the relationship between x's and y's in this case. So polynomial regression is this formulation, a of x squared plus b of x plus c. This formulation is a quadratic polynomial that we'll be using, and quadratic because x squared exists within this framework. So phi of xi is a power function. It's all it is just a power function of your input variables. In other words, this here is x and this here is y. Right? This is how we are looking at a graph. Every ordered pair is x1, y1, x2, y2, x3, y3, and so on. When we are discussing these kind of kernels, what happens is instead of, again, we are moving into a different dimensions. We are moving into a higher dimension. So in this case, your y will be this axis, x will be this, and this will be something called x squared. Another dimension is going to be x squared in this case. From a two-dimensional graph, you now have a three-dimensional graph. For this quadratic function, we now have a three-dimensional graph. It's hard to draw this for a three-dimensional thing, but let's say the hope is that in this case, you have your x's. So in this case, it's x squared 1, comma x1, comma y1. That's how I'm defining all this. In this space, your line is a three-dimensional line. Even though it is a nonlinear function, in the first graph, it's nonlinear here. In this point, it is going to be linear. That is how we are creating this kind of a polynomial regression. The axis that we're going to be using, if it's x squared, squared version of my input data feature, then it is going to be a polynomial regression. Hopefully that part is clear. So you have x cap, yi equals theta naught cap plus theta 1 cap x1, xi square, and so on. Exact same formulation what we had during linear regression, except that instead of xi, you have phi of xi. And phi is this power function on top of my feature, so it's going to be 1 x1 square until xi to the power m. M is the degree of the polynomial. So in this case, it was very easy to show a quadratic polynomial. In other words, it's just a power of 2. Power of 3 would be a cubic polynomial, but we won't be able to show it in the three-dimensional space because y also occupies one of these spaces, so we won't be able to show it. It'll become a four-dimensional graph. But essentially, if it's a three-dimensional polynomial, it's a cubic polynomial, and so on. You can have m degrees, and that is what this is showing us. There's m degrees that exist within this polynomial. And of course, 1 is for the theta cap, it's the bias that we add. Theta to the theta m is the features. Every single feature is being weighted by a certain parameter. In this case, that is given by theta. And of course, you still have epsilon. Look at the epsilon dimensionality. Epsilon is n. In other words, epsilon is the error, right? Every data point has an error associated with it. It doesn't depend on which kernel, which dimension you're going to. It's just that in the original space, there was an error associated with it. So if I were to go back here, is there a way? Apparently not. So let me redo graph with a. So if I have x, and this was my output, your epsilon is always going to be something like this. So this is epsilon 2, this is epsilon 1, this is epsilon 3, epsilon 4. So essentially, the number of epsilons that you're going to have is independent of the dimensionality of the polynomial. Rather, what is important for the epsilon is the data point itself. Every single data point has an error associated with it, and that's why it goes from epsilon 1 to epsilon n in this particular case. Even though theta is in a different representation space, it is weighing your data. Your epsilon is still going to be based on the original representation space that we were using it. Hopefully that part is clear, the difference between m and n, why epsilon and theta are in different dimensions. Any questions until this point? Yes? Yes, degree is a hyperparameter that we need to set. We need to set it beforehand itself. So that was for a single feature. Given just x, I could have an x square as my another axis within the graph, and we are able to construct it, and we are able to create this kind of a nice function, nice relationship between the input data, which we are going to call as x's, and the output data, which is y's. But we might have more number of features, right? In Iris dataset, for instance, I believe there are 4 features that we can use. So how do we use more when there are more number of features? The question is, how do we create this kind of a polynomial regression? And this is where we start running into a few technical errors, technical details, or technical problems, let's say, which is the computation part. So let's talk about like very simple 2 features that can exist. So x1 and x2. It could be the sepal and the petal width. Those are the 2 features that you can have in Iris dataset. When you want to create a polynomial regression on just those 2 things, we start running into this. Just look at the amount of data that you can have. You can have x11, which let's say is the sepal width, and x12, which is the petal width. SW and PW, I'm just using it from the Iris dataset. Now, when we are taking parse of our features, there could be the sepal width whole square. There could be the petal width whole square. And then we'll have another function as well, which is a combination of the 2 things. Think of it as a plus b whole square. That is how we are generating these polynomial coefficients. So a square b square plus 2ab, right? The ab is a multiplication of the 2 features. So in this case, it's width multiplied by the petal width will be the other feature. And essentially what you have generated is a set of 1, 2, 3, 4, 5, 6, 7 features that you need to learn, I guess it's 5 here. You need to learn 5 theta caps in order to get the outputs. Actually, is that correct? 1, 2, 3, 4, 5, 6. Oh yeah, so theta naught to theta 5. So there are 6 number of features in a higher dimensional representation space that you need to learn, and that is where the theta naught to theta 5 comes in. Again, you'll have n number of data points to choose from. In Iris dataset, it was 150. Right? So now you start seeing that there is some kind of a computational challenge that goes into constructing this kind of matrices and finding the solutions for the best possible theta cap in this particular case. So from now on, whenever we are using the letter P, it's for the number of features, and M is the degree polynomial that we will be using. So let's look at the least square cost formulation for this exact setup. It's very similar to before. You have y equals x theta cap plus epsilon, which is the exact same thing that we did in linear regression as well. We take some distribution for epsilon. Again, we are going to be using the normal distribution, which we have over here. So the likelihood function is going to be the same. Everything is the same as linear regression, except one thing, which is that every time we have xi, we usually put a phi of xi on it. Now again, most of the things are similar to linear regression, because we are assuming that in a nonlinear representation, in a higher dimensional representation space, my regression function is going to be linear. So every other part of this is going to be the same, as long as we take x to be phi of x. That is the only difference that we're going to have in the formulation of least squares between the linear regression and between polynomial regression in this case. So even the least squares cost function is going to be the same, exact same, except of course you have phi of xi minus yi whole square instead of theta transpose directly multiplying with xi. going back to what we had before, we have two choices right now. One is we can use something like gradient descent in order to find the optimal parameters. Now that we have a cost function, we know what the optimal cost function needs to be. So we need that loss function to be near 0, or we need the gradient to be 0. And we can get that using gradient descent at this point. Or we can do the same thing that we did last time, which is find an analytical exact solution. And that is something that we'll be starting with, which is the normal solution. So let's look at if normal solution is actually possible in polynomial regression. Let's start by putting the same functionality as before. Your loss function is least square solution. So 1 by n phi of x theta cap minus y transpose phi of x theta cap minus y. This is the exact same thing that we started off with the least squares formulation for linear regression. And the output is this. The most optimal set of functions, the exact solution, is given by phi of x transpose phi of x inverse multiplied by phi of x transpose into y. This is the same thing that we had derived last time in linear regression as well. Only difference, of course, is what I had mentioned before, which is x is phi of x. Nothing, there's no difference at all. You can go through the exact derivation that we did in order to get this optimal solution, this exact solution based on this normal equations. So let's look at this equation and start looking at the dimensionality of the output, or the best optimal theta. So phi of x, right? It is a sample that, let's say, had p features that we have now moved it into m degree polynomial. So in other words, it's 1 of xi until xn. So the theta itself will be in r of m plus 1 term. If I go back here, where was the second degree? Yes. This was our output, right? So based on the fact that we had, maybe not this, yeah, this one. This is where we had the output. You can take m to be 2 in this case, and what you'll notice is that you'll need theta naught cap, theta 1 cap, and theta 2 cap. In other words, you'll need an m plus 1 dimensional space in order to represent your theta itself. So if you have one feature, you need m plus 1 number of parameters in order to find your output. So let's look at it from a more general setting. If we have p features, so xi itself was in p feature space, then the output is going to be p plus m features, right? If I go back to this case, yes, in this particular case, we had about m equals 2. We had m equals 2 and p equals 2. So the output that you saw was theta naught cap, theta 1 cap, theta 2 cap, 3 cap, 4 cap, and 5 cap, right? So your output, excluding the bias, would be p plus m, which is 4 in number. And this is a very common feature within something called, if you look at the polynomial equation and the number of coefficients that you have, essentially you will be looking at this. P plus m, c, choose m set of coefficients that you require in order to model your polynomial function. This is the number of features that are, or the coefficients. Like if you have ax squared plus bx plus c, for instance, a, b, c are coefficients. So the number of coefficients that you need in order to find your polynomial equation is going to be p plus m. I think there's a minus 1 as well for the original functionality, but then we add a bias, so there's a plus 1 at the very end. P plus m, c, m in this case, right? So if we look at the 3-degree polynomial, which is a plus b plus c whole square, let's say, cube, sorry. So a plus b whole cube in this case, because we are using 2 features and 3rd-degree polynomial. What you'll notice is that you'll have some bias plus 1. This is a plus b plus c. Sorry, this is a plus b plus this is ab. This is a square, b square, a square b, ab square, a cube, and b cube. These are all the different coefficients that you need in order to find your polynomial equation. And what it reduces to is 5 choose 3. This is the number of equations that you need in order to get your solutions. The problem here is not the calculation part, but what it tells us about how we need to create our matrices. Now let's go back to this formulation of least squares that we had before. So in this case, we see that there is an inverse function, right? Phi of x transpose phi x and we need to take an inverse of this function. The entire field of optimization, one of the main reasons it exists is that taking inverses is not easy. In fact, for a very simple case, I have this in the next feature. For a very simple case, when p is equal to 50 and m equals 3, this, again, it's a very simple case. We usually think of medical data, for instance. The amount of data that you generate every time you visit to the doctor's office and compound that with the number of times you go to the doctor's office, right? P of p equals 50 is a very small number. Generally, we have these high-dimensional data sets where p is going to be extremely large. Or if you look at images, for instance, if you take each pixel as a feature, just a very small 224 cross 224 image is going to have, even MNIST data set, which was 28 cross 28, has 784 features. So so the number of features that can exist in my machine learning module is very, very large. And even with p equals 50 and m equals 3, the inverse is going to be about 23,426 multiplied by 23,426. The day size of your matrix in order to calculate this inverse is going to be very, very large. And one of the main reasons that we will not be able to use the exact solution using normal equations is this idea. And there are many ways, by the way, where people have devised ways in order to find these inverses. But in most cases, especially when we come to large data sets with deep learning, we cannot rely on on normal equations and exact solutions in order to find our optimal parameters. Rather, what we need to do is have something called gradient descent, or have an algorithm like gradient descent in order to find our solutions. So the other parts of this is the same thing. P of m choose m is going to be the size of one number of rows, and the same because you're doing phi of x transpose phi of x. It's a square matrix, which is going to be p plus m choose m as your data set output. Even storing this size data within your memory is going to be very difficult, especially if you're looking at calculations within the RAM and you're doing it across iterations. It is going to be very, very hard to try to justify using these kind of straight up inverse algorithms. And this is where we need to start thinking about gradient descent and if there are other ways of trying to find these solutions. Any questions? All right, so gradient descent is something that we saw in classification as well, but we'll go into a little bit more depth in this case in regression. The idea is exactly the same as before. We have some kind of a loss function L of theta that we have defined. Let's say the least squares regression, the least squares framework that we have defined. There will be an optimal set of parameters theta, here theta, that is going to give us zero loss, or the minimum possible loss. Zero loss is achievable when in classification, when there is non-separable data, zero loss is achievable. In regression, when my error is zero loss is achievable. But that is again just a pipe dream. We never have non-separable data in real life, so which means that in classification we'll never have zero loss. Rather, what we need to do is have this kind of we'll find a gradient which is horizontal to my theta, and that is going to give me d of L by d of theta is equal to 0. My gradient has to be 0 in classification, which will allow me to find the best possible optimal set of parameters, so that even with non-separable data, this is the best your algorithm can do, essentially, is what your gradient 0 is going to be telling us. Same thing with regression as well. Given a certain tolerance, epsilon, which is, you can think of it as noise, but in gradient descent, it's not exactly the same. It's a tolerance with respect to gradients. But given this tolerance, if my gradient is below this particular tolerance, then I'm going to say that I've achieved the best set of parameters available to me, and that would be the output of your gradient descent algorithm. again, the goal will be very similar. We'll start off with some kind of an initialization of my parameters theta. It can be a very random set of initialization. You don't have to be very specific in taking which set of parameters you want. The hope and goal in gradient descent is that given any set of random parameters, you'll be able to move to this kind of a minimum in a number of steps. And this steps is what we are seeing here. At every step, or we can call it iterations for now, but then later we'll call it epochs. But at every single iteration, you're moving towards a certain point where your gradient is going to be 0 or within a certain tolerance. The derivative is usually the negative gradient, points to the direction of the greatest rate of decrease. The opposite is usually what we use in terms of trying to understand the definition of gradients. Gradient is essentially a tangent. Given a certain curve, it's a tangent, and it points in the direction of the ascent, the fastest, wherever the fastest movement is for that loss function. The negative of that is going to do the exact opposite. It's going to tell us which is where the minimum of the loss function is going to exist, and that's why we'll always be using minus, right? So you saw in your homework that there was always, whenever you have W, it's a W minus of gradient multiplied by some learning rate. That's because we are trying to move in the negative of the direction with the highest, or the negative of where the loss keeps on increasing. And by doing that, we'll come to the minimum. So a couple of things before going into the derivation of itself. So the least cost formulation is given by 1 by n sigma 1 to capital N xi transpose theta minus yi square. This is the same thing that we have seen before. Capital N is the number of points or the number of data you have. For instance, Iris is going to have 150 data points. Your derivative with respect to the cost with respect to theta, whenever we do gradient descent, if our goal is to optimize towards a certain set of parameters, we always differentiate it with respect to theta. Or W or B, whichever you're calling it, whichever you're using at that particular point in time. So differentiating this function, we have this one here in the box, which is 2 by n sigma 1 to n xi transpose theta minus yi multiplied by xip. Again, this is just application of the chain rule, essentially. We're using theta p here in this case, at least to just show it, because we want to show it in terms of how it looks like in this matrix form as well. So if you don't look at it as a set of equations, and so this is the equation here, which is the same as this. If you don't want to look at it as a set of equations and want to put it in terms of a matrix, this is how it's going to be. At every element within your matrix, each row is dependent on your features. So the first row is, there's a partial derivative with respect to theta naught, second row with respect to theta 1, and the final row with respect to theta p, which is the final parameter that is multiplying my feature set. So gradient descent step is the same thing that we saw before, which is theta t plus 1, which is at a particular iteration t. I want to get a better set of parameters. So that is the better set of parameters is given by theta t plus 1 equals theta t minus of alpha into delta theta MSE of theta. So alpha is the learning rate. So for now, I think in homework 2, you were just given, okay, this is the learning rate, you can use it. But alpha is in fact a hyperparameter. And at the end of this class, we'll see how changing that alpha, or when we need to change that alpha in order to get a better algorithm. So the other parts of gradient descent are very similar, which is theta t plus 1. This is the thing that we just saw. We also have access to the gradient at this point. For polynomial regression, your output is going to be the same. The difference, of course, is that instead of taking x directly, which we were doing at this spot, instead of taking x, we take phi of x. So whenever there is x, all you need to do is just replace x with phi of x. So in this case, it's going to be phi of x transpose multiplied by phi of x into theta minus y is our gradient method. Again, what has happened when you have taken phi of x is that the number of features has increased, right? So instead of just having x1 and x2, you have x1 square, you have x2 square, and x1 into x2. In other words, now you have 2 that you originally had, plus x1 square, x2 square, and x1, x2, which is the 3 new ones added because of the kernel and the bias. So in overall, you'll have these 6 number of parameters that you will be using. So you have now the representation space is n multiplied by p of m, p plus m choose m. This is the data size, the size of your data phi of x. Again, this seems big, but compare it to the other thing, which is p plus m given m. The size of the matrix and the inverse of that would be much, much higher than what we have in this case. So there are a number of ways in order to do gradient descent. Until this point, we have looked at x as a monolith, that we need to take all of x in order to calculate the gradients. We need to use those gradients to update my parameters. That is all we have been doing until this point. But in many cases, it is not possible to do something like that. Because look at this size of phi of x here. N is the number of data points I have. As long as it's something like iris datasets where it's just 150, it's fine. 150 points is something that we can take into consideration quite easily within our memories, and it'll be easy to calculate my gradients and update my parameters. But at a certain point, capital N is going to become very, very large. The most common datasets used for analyzing images is something called ImageNet dataset for recognition. It has about 1.3 million images. So capital N in that case is 1.3 million. And in the project thing, when we saw the number of masks, it was 1.1 billion masks that are used. So in these cases, we cannot use gradient descent as is. So we have some strategies that we are going to be using in order to get those kind of gradient descent. And batch gradient descent is what we have discussed until this point, which is we are going to take all possible data points to create the gradients and get our solution. There are 2 other cases, which are called stochastic gradient and mini batch gradient descent algorithms. In fact, if you take an optimization course, each of these things is a lecture. Each of these things is at least a chapter by itself, just to talk about what they are and how they relate to each other. But this is a fundamentals course, so we're just going to be covering within the next 3 slides all of these things. The math behind them, we won't go deep into it, but it's very fascinating. If you are interested, there's many books that go into details of each of these algorithms. Let's start with the overall thing that we have seen. Till now, we have just called this slide as gradient descent, but it's something called batch gradient descent. If you look at the level curve, so this plot here is something called level curves. Every single point has the same loss. That is what a level curve in this case means. It's sometimes also called a contour map. If you're using Matplotlib or MATLAB and you want to create these kind of graphs, it's called a contour map. The goal of that contour map is that every single point at this, in this, let's say, circle, has the same loss function. Think of it as a kind of a funnel. This entire thing is a funnel where blue is at the lower end of the funnel, and which is this? I think this is orange. Hopefully you can see that, yes. The orange part is at the edge of the funnel. And you're looking at the distance from the very bottom, at the tip of this kind of a funnel. Every point in this section of that funnel has the same value. In this case, it has the same loss. So all these black points have the same loss. All these green points that I'm putting here have the same loss, and so on. So in other words, what I'm trying to say here is that I am looking at this image, and instead of thinking this as a 2D image, I'm thinking of it as a 3D image, and I'm taking a cross-section of this 3D image and plotting it as a circle, right? If you think of it, the other thing as a funnel and take a cross-section, this is what it means. So every point here has the same loss. In other words, at this thing, this point and this point has the same loss function. It's just they're moving in different directions, which is fine, but the loss value itself is the same. And that is what this contour plot or this level set plot is telling you. We start off at some random point at the very top, which we did here as well. At this point, we started off at this very random point up top, and our goal is to move towards the bottom here. And that is essentially what this is doing. If you look at this in a 3D way, you might think that the loss kind of is increasing and decreasing, but it's not. It's just traveling in this curve. So this curve essentially is this parabolic function that exists in this case. So for a higher dimensional, in a higher dimensional space, you must start thinking of it in a hypersphere rather than from like a two-dimensional graph that exists. The good thing about batch gradient descent is that you can get this simple kind of a parabolic path and come here to the optimal set of parameters. And as soon as we get to the optimal set of parameters, we say that convergence has been achieved. That I have found my optimal set of parameters. They exist at this spot, and they are theta star, which is my supposed to be my output. And this is essentially what convergence is going to be. Now, generally, as I mentioned before, we want this to be 0, but in real life, it's never going to be 0. Hence, you'll define something called a parameter called epsilon. And this epsilon is going to be something that we'll call tolerance. If the outputs, my theta star has a certain value, when you multiply that, when my gradient delta theta MSE of this theta, it gives me a certain value which is lesser than my tolerance, we are good. So that means that we are done with our gradient descent algorithm. We'll say this is the best possible thing that I can achieve and move on to the next challenge or problem that is there. So that definition here of epsilon is called something called the tolerance, right? And I'll talk about smoother convergence. Maybe this will make more sense when I show you the graph for stochastic gradient descent. Once we see that, you'll see why this is smoother. Any question with respect to batch gradient descent? This is exactly what you did in homework number 2. This is all that you have done. Yes?
How do you choose a loss that you know you'll get the loss?
So that is something that we're going to call convex loss functions. Anything convex is, this particular loss here is convex, right? It's because at every single point, I guess the details of it are beyond the scope. Essentially, you need to create something called an epigraph or a tangent, and those tangents at every single point has to contain the entire function. That is how we are going to define this thing. Now, maybe that isn't very clear. Let me show you something that is non-convex. So this is a non-convex function. If I define some kind of a tangent, part of the loss function is above and below. It doesn't contain the entire graph. Again, what I mentioned is not exactly correct. We need to define something called an epigraph. But essentially, what you see here is a convex function, and what you see on the other one is a non-convex function. This is a non-convex function. Ideally, we want to define these kind of convex functions, and there are many number of convex functions that we usually use. Everything that we have seen, like least squares, hinge, is all convex loss functions that we will be using. Any other questions? All right. So as we discussed, it is very hard to do it across capital N, which can be 1.3 million images. Right? It's not possible to, in fact, store all this and calculate gradients for all these data. So what we do is something called stochastic gradient descent. In this case, we randomly pick one data point, let's say one image out of the 1.3 million data point we have, calculate the gradient for that, and update our model, which is going to be theta. And we do it, and this is what we'll call one iteration, but then we have to take all 1.3 million images into consideration, right? So we will do the exact same thing 1.3 million times. Every single iteration, we are going to choose one data point, we are going to calculate its gradient, and we're going to update the theta parameters. And after that iteration, we pick another point, which is within the 1.3 million. After that, one more. So we do this 1.3 million different times to complete one epoch in order to go to find our solution. In other words, so in my batch gradient descent, I was moving from hopefully you can see this point to this point, and this was done with n number of images across one epoch. Right, so this moving from one point to other point happened when I looked at all possible n images to get the gradients and update. I can show the same thing here as well. You move from 1 to here. Essentially, when you're taking a step, it's across all n data points, you get your gradients and you can update. The difference that we are doing in stochastic gradient descent is that, let's say in this case, I have about 4 data points that I'm using. These 4 combined is one epoch. So epoch, and there's capital N, I'm just showing in this case as 4. Right, so I take a single data point, I move my parameters theta. Now those might be very incorrect, and most probably they are, because at a single point you'll never be able to model your entire function based on one data point. That's the goal of having a lot of data, right? You want about 1 million images, or you want these million data points so that you can model a good function. Now I'm telling you that by just taking a single data point and updating it, you'll get a solution. So there's a lot of theory and math that has gone behind why something like stochastic gradient descent works. In fact, stochastic gradient descent sometimes works even better than gradient descent, because in gradient descent we'll never have this nice, we'll choose a convex loss function, but when you actually look at the data points, they don't adhere to this loss function. It's in reality, the actual function is going to be something like this. So in those cases, sometimes you want randomness within your algorithm so that you don't get stuck in these kind of local minimas. You want to get to this spot, which is what we're going to call global minimas. Local minimas essentially mean that given a very small set of parameters theta, there is always going to be a minimum. If I tell you, if I constrain your theta and say that it could be only between like 0.2 to 0.5, maybe there is a value called 0.345, which is possibly the best. But if I had not given you that constraint and said, give me any good theta that you can find, it probably would have found like 0.85 or something. So in this case, this would be 0.85, while in this constrained space, this would be 0.345. Right? So sometimes when there is this randomness that is involved, you want your gradient descent to not be exact at every point. You want it to move in the opposite directions incorrectly, so that maybe after n number of, not n, maybe after some z number of epochs, you'll be able to get to the point, which is not the exact solution, but it's somewhere near this point. This is essentially what stochastic gradient descent keeps telling us, which is that I randomly pick some ith sample, and based on just that one sample xi, I'm going to update my theta, which is I'm going to update my parameters, and I do this for n iterations. Right? So that is, I need to take all my n data points into consideration. I do it for n iterations and move this n times, and that will be one epoch. And this I can do until convergence. In other words, I can do this for k epochs. I can do it across k epochs in order to find my solution. In other words, the number of times you're doing this calculation is k multiplied by n. If I have k epochs and I have n data points, at every epoch I need to take n data points into consideration, and I need to do it at every single epoch. So it's going to be k multiplied by n number of updates that I'm going to do for my parameter space. Any questions about stochastic gradient descent? Yes?
So we spoke of two hyperparameters, k epochs and the tolerance, right? So
yes.
One of those, or like what's the...
So the tolerance is something usually that we always choose in the beginning. It's very much application dependent. We know for a medical data set, for instance, our tolerance has to be very low versus something like image recognition. Let's say you're using Amazon app in order to find, in order to recognize something. It's not as important to do it versus this. So epsilon is not very difficult to find. Usually you'll be able to get a good value. The epochs, on the other hand, it's very much dependent on learning rate. So you have these two hyperparameters that are dependent on each other. So alpha is also another hyperparameter. At the end of this class, I'll show you exactly what happens. And based on that, we usually choose our epochs. And I'll talk a little bit more on that in a while. Yeah. Any questions? So next is something called mini batch gradient, which is a combination of these two things. Look at the original batch gradient descent. The good thing about batch gradient descent is that in a small number of epochs, in n epochs, you would be able to come to a certain conclusion about, okay, this is my optimal set of parameters. The problem, of course, was the fact that you needed n of these things. You needed to calculate based on n such data points. The good thing about stochastic gradient is that you just given a single data point, I can update my parameters. But the problem is the number of times I need to do this update. It's k times n. It was n in gradient descent, now it's k times n, right? Because number of epochs is k and iterations is capital N in this case. Mini batch gradient descent kind of tries to combine the two things, and this is generally what we use in any deep learning modules, which is we're going to take the entire data set and convert it into a set of mini batches. If I'm given 1.3 million images, 1000 is, depending on the size of your RAM, either 256 images or 1000 is the usual thing that you would take, especially in visual processing. And you're going to use that, either 1000 or 256, as in order to calculate your gradient and update your parameters. In other words, you sample a subset, x of s, of size b instances. This is the 256 or 1000 that I just said. Let's just go with 256 for now, just to try to understand, because it usually works with almost all data sets. So given these instances, these number of instances, you calculate your gradient based on just these x's. Right? In stochastic gradient descent, you were doing it on a single point, xi. Now you're doing it on b number of points, which is capital Xs. And you do the exact same update, which is theta t plus 1 equals theta t minus alpha into your gradient. So you're doing the same thing, except now instead of doing it on a single data point, you're doing it across b data points in order to find your gradients and then update your parameters. Of course, you have to do it n divided by b iterations, because you want to cover the entire data set. You shouldn't just stop at b parameters or b points to say that, okay, I've got my parameter update, I'll move on. No, each epoch you have to cover the entire data set that may exist, and hence you need to do n divided b iterations in order to find this solutions. So the number of epochs is going to be lesser. It's not going to be k epochs as before. It's going to be n divided by b, and you still multiply it by how many ever iterations you need to do in order to cover the entire data set. If you see the convergence path on the contour plots, it's something halfway between the batch gradient descent and the stochastic gradient descent, and it makes sense. In the beginning, when it's not as dependent on the learning rate, it is going to look like the batch gradient descent, but as soon as learning rate comes into picture, you need to start scheduling it, and it looks like this. That last part may not make sense what I just said, but I'll come back to this slide when I explain what learning rate means. Any questions? It's basically a trade-off between computational complexity and finding optimal parameters. I don't know if I mentioned this, but in both stochastic and mini batch gradient, you're never going to end up at a certain point. You're going to keep moving around this point, while in batch gradient descent, you're going to stop at an exact spot. Any questions about yes?
Do the batch gradient descent or the stochastic version of this, if you're just doing it on one sample, how do you then combine all those results in order to have, because you might have for different samples vastly different convergences.
Yeah. So you don't do it you don't converge to a sample. You take a single sample, you find the gradient, you update the parameters, and it's going to move from this point here to this point. It's incorrect. It's going in the opposite direction that you wanted to go, but it's perfectly fine, because the hope is that at every point we are moving in a certain direction that is then going to later help us. Like every point adds to this thing. So the next one also is going to be very different, right? But maybe you'll have a fourth point which is going to come closer to this. There's a very small, if you see from here, I can't even do it, but you see that there is a small point that is going towards it. So in other words, you don't take a single point and optimize it towards going into convergence. Rather, you take a point, you update it. You take another point, update it. Another point, update it. You do it across the million data that you have. That is one epoch. Next epoch, do the same thing. Take the first data point you're taken and in the beginning, update it. Update your model based on that point. Does that make sense?
So this whole thing here would be like one, epoch?
Yes, this is all of the epochs. And this here, if I have 4 data points, this will be one epoch. This will be the second epoch. Right? So again, it's very important. An iteration or epoch, you're not taking a single data point and converging it. Rather, at that point, you're just updating your parameters and you come back to the same point in the next epoch. You come back to the same point in the next epoch and so on. So one epoch, you're just taking the million images or capital N number of data points that you have and updating it. Not towards convergence, but to whatever you get. In this case, it's not converging at all. Maybe it's even worse than it was before. Perfectly fine. Then that just means that you need to change your learning rate or some other hyperparameter in order to move towards the optimal set. Yes?
So if you have like a batch set of samples, would you just like split it up?
Can you repeat the question, sorry?
So you have like a batch set of samples for this one, are you like splitting it up?
Like random pieces, or are you trying to?
Bad set or batch set? Batch set of samples. So okay. So if you have so you're defining your batches, right? So if you have million n, you can define, let's say, 1,000 different batches. So that means that every single batch will have 1,000 set of data points. And for those 1,000 set of data points, you can do calculate your gradient, update your parameters. Then for the next batch, mini batch, you update it again. Next mini batch, update it again, and so on. That's how you would do it for the mini batch gradient descent. I'm sorry, I don't know if I answered your question. I did. Okay, that's good. Any other questions? Yes.
Stochastic first and then do the batch later once you reach, like, because the batch actually gets you into a fixed point.
You can. So you're saying, can I change my strategy in the middle? Can I start off with something like stochastic gradient descent? After it has moved to a certain point, can I do gradient descent? Yes, you're more than welcome to try any set strategy to do that. But the main point still stands, which is gradient descent, the batch gradient descent. You'll still have the same number of endpoints. Right? It's not that when you do a stochastic gradient descent for, let's say, 5 epochs, you would have optimized for for like 50,000 data points or 50,000 images. Those still are not there, because after the first set of stochastic gradient descent, you're still at this point, and none of the data points have been optimized yet. Again, so you're not taking a single point and optimizing it. Rather, in an epoch, you're just working on everything separately, and you're coming back to that data points, all those data points in the next epoch again. You won't, stochastic gradient descent is not about optimizing until the very end for one and going back. No, it is that at every epoch, we are looking at all n images separately. It's similar to the naive-Bayes assumption, where you're looking at all data points independently and then multiplying it, right? So in this case as well, we are looking at all data points separately. We are changing our parameters and going back to the parameters all over again. Going back to the data points all over again in order to change my parameters. Hopefully the pseudocode should be helpful. So I encourage everyone to just go back and just look through the pseudocode, because that differentiation is very important. Stochastic gradient descent, we are not optimizing a single data point towards convergence. Rather, we are going back to the data point again and again at every epoch in order to try to make it better than what it was before. That's it. So this is the difference between an epoch and an iteration. It's more easy to understand the definitions when you look at it between batch gradient descent, stochastic gradient descent, and mini batch gradient descent. So in one iteration, the entire data set is processed for batch gradient descent. But in stochastic gradient descent, at one iteration, a single point is, we are taking the gradients, right? So at each step, we are taking the gradient descent step for that data point. Mini batch is somewhere in between. Your data set, let's say, is divided into B batches, and we'll be using that as our number of batches. Epoch, in gradient descent, it's completed in a single iteration, because in every iteration, I'll be looking at all endpoints together. So that means that every iteration is an epoch for your gradient descent. But stochastic gradient descent, n iterations, when all data samples are processed, will be one epoch. So every single time I'm looking at a single data point, and at the end of all n data points, I'm going to have one complete epoch within this framework. Again, it'll be something in between for the mini batch gradient descent, which is there'll be n divided by b iterations. Capital N is the total number of data points, b is the number of batches, so it'll be n by b, yes.
Are the weights updated after one iteration or every iteration?
Every iteration, weights are updated. For all three. After every single iteration, the weights are updated.
And then after an epoch, is an epoch just significant because it means that all the data has been processed,
Yes.
but there's no different calculation that occurs after the epoch completes, it just resets?
Exactly, yes. The last part, I'm not sure what you mean by just resets. If you mean that you go back to the first, yes, you go back to the first and process everything again. Exactly. So an epoch essentially means what you just said, which is that all data has been processed. After a completion of one epoch, that means all data has been processed, or your model has access to all the gradients with respect to the data points within my training data. That is essentially what an epoch means. So all gradient descent methods, they end up near the minimum. Batch gradient descent stops at the minimum, but the stochastic gradient and the mini batch gradient kind of walk around. They move around the optimal point, which is fine again. It depends on our tolerance epsilon that we have defined to say that, okay, this is something that is acceptable or not acceptable. Last part is very important, which is stochastic gradient descent and mini batch gradient descent would reach the minimum if a good learning schedule is available to us. So let's look at what that means. Learning schedule is the learning rate, the step size that we are using. Step size, till now we have looked at alpha as, let's say, some deterministic quantity, which is 0.5. But this is not a good idea. In most cases, by sticking to a single learning rate, we are actually handicapping ourselves, right? So look at this case. If your alpha is very, very low, like 0.01, let's say, your movement between your iterations, between your steps is going to be very low. So across, you need to do the same calculations and like very large number of times if your alpha is very low. But on the other hand, if alpha is like say 1, it's very high, this might happen. Your first thing might move to here, then it might move here, and so on. Right? Your alpha is extremely high in all these cases, which basically means that even though you're coming near the minimum, you will never be able to get it, because after this point, based on the same learning rate, it can actually go here. And it can go away from what the minimum was. It has no idea what to do. So in this case, what we do is that we try to schedule these kind of learning rates. In my first 50 epochs, I'm going to use something like 0.1. In the next 50 epochs, I'm going to use 0.01, or I'm going to divide it by 10. In the next 50 epochs, I'm going to divide it again by 10, essentially. This is what I'm saying, that in the beginning, you might want to come to a convergence as quickly as possible, so your learning rate will be high, but then you'll schedule it in such a way that after a certain number of epochs, you'll reduce it. And there are a few algorithms which tell you how best to schedule your learning rate, or what the best learning rate is, what the best direction is as well, but we won't cover into that. There's a lot more theory in optimization, but we won't go into that. But in practice, this is more of a, you see a few examples to see how best to do it, and then you'll be able to get your ideal result. Right? So another reason why the step size and learning rate matters is this idea of a local minima. So if you have a single minimum here, it's very easy to get to this minimum using your gradient descent. But in most cases, this is how your cost function is going to look like based on your data. And it could be many reasons that your data is looking like this, right? It might be that your outputs are incorrect. Maybe there were, as I said, 1.3 million images. Somebody has looked at an image of a cat and thought that it was a dog and mislabeled it. So that creates a huge problem within my loss framework at this stage. Even though my model thinks that it's a cat, my label is that of a dog. So there is a discontinuity at that point. So there's multiple reasons why your convex loss function can actually be non-convex. So in this case, what happens is that if your learning rate is very low, it'll never be able to get out of this kind of local minimum. So what you need to do in that case is in fact have a high learning rate so that it moves hopefully something like this and so on. It will be able to randomly, it will be able to hopefully come to the global minimum. And in fact, one of the reasons that stochastic gradient descent is better than gradient descent when you come to these kind of large scale algorithms is this very reason. In deep learning, mostly you'll find yourself in local minima a lot of times. But if you do stochastic gradient descent, it'll move out of that local minima because it is incorrect. The gradient is incorrect in many instances. And if this were in fact the global minima, it is going to come back because of across the different points in the data set, it will tell you to come back to this particular spot. You'll take more iterations in order to get to the optimal point, but you will get to the optimal point based on these kind of random sequences that exist. Again, this is more how the regression algorithm is going to look based on different alpha parameters or learning rates that you can choose. Feature normalization, very important again. Whenever we have these kind of gradient descent algorithms, feature normalization is very, very important in the beginning in order to get a good output. The last part is something that I'll cover next week. So it's just a comparison between the three things that we have, which we discussed. We'll start from steepest descent from next Wednesday. Thank you. So that's the end of this lecture.